In this video, we're going to be talking about one-to-one functions and inverse functions. A function f with domain A is called a one-to-one function, sometimes written 1-1, if no two elements of A have the same image or output value. Here are some alternative ways of saying that. The first way is f of x1 is not equal to f of x2 whenever x1 and x2 are not the same value or equal to each other. Another way is every output of f of x corresponds to exactly one input. In an earlier section, we defined a function g that mapped a person to the city that they were born in. Although it is a function, it is not a one-to-one function since several people are born in the same cities. We talked about another function in a previous section that told us how much we would have to pay if we went to Oregon and were filling up our car with gasoline. Assuming that gas costs $4 per gallon and you are tipping the attendant $7, then if you get X gallons of gas, you would be paying C of X is equal to 4X plus $7. This is an example of a one-to-one function because every price corresponds to a unique amount of gasoline. So just visually here, we have an example of our g of x function, and it turns out that Zendaya and Kamala Harris were both born in the city of Oakland, and so this tells us that g is not one-to-one because we have multiple inputs mapping to the same output. Now, alternatively, in the c of x function that we are looking at here, this is a one-to-one function, again, because if I know that I'm paying $11, there's only one possible amount of gasoline that I could have gotten based off the scenario, and it would be 1 gallon. So the only thing that maps to $11 is 1 gallon. We don't have multiple things mapping to the same output value. So that tells us here that this is one-to-one. So we're probably used to talking about the vertical line test. Here we're going to talk about the horizontal line test, which says a function is one-to-one if and only if no horizontal line intersects its graph more than once. Let's put this into action. Example 1 says determine if the following functions are one-to-one. Part A says f of x is equal to x squared. So I've gone ahead and sketched a graph of what f of x equals x squared looks like. And if I applied the horizontal line test, if I draw any horizontal line that's above the x-axis, what's going to end up happening is that horizontal line is going to cross our function graph at more than one location. So this fails the horizontal line test. So f of x equals x squared is not one-to-one because it fails the horizontal line test. Let's try part B, where we have f of x equals x cubed. So again, I've gone ahead and I've graphed f of x equals x cubed. Now here, if I draw any horizontal line, it's only going to cross my graph at most one location. So here, 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 here. So what this tells us is that f of x equals x cubed is a one-to-one function. It passes the horizontal line test. You might be asking yourself, how do we determine if a function is one-to-one without looking at its graph? Sometimes we're given a function and we don't have a graphing utility or we don't know what the graph of the function looks like. So let's put this into practice. Example 2 says determine if the following functions are one-to-one. In part A, we have the linear function f of x is equal to 3x plus 2. So here's what I'm going to do for part A. I'm going to say basically suppose f of x1 is equal to f of x2. And what we're going to show is that this is only possible if x1 and x2 are equal to each other. So let's go ahead and evaluate f of x1. That means that inside of my function, anywhere I see an x value, I'm going to replace it with x1. And then same thing on this side, I'm going to Anywhere I see an x, replace it with x2. Okay, so what I'm going to do now at this stage is I'm going to subtract 2 from both sides of the equation, and then that's going to give me that 3x1 is equal to 3 times x2. And then from here, if I divide both sides by 3, I end up getting x1 is equal to x2. So what this is saying is that if I have two different, or excuse me, if I have the same output value, they're only able to be the same if the input values are also the same. So algebraically, this shows that f of x is 1-to-1. All right, let's try it for a different example, because you might be looking at this algebraic process and saying, isn't that going to happen every single time? Not quite. So let's look at example B. Okay, so I'm going to do something similar. I'm going to suppose g of x1 is equal to g of x2, and then I'm going to go ahead and plug x1 and x2 into our function. So that's going to give us x1 quantity squared minus 1 is equal to x2 quantity squared minus 1. Now I'm going to add 1 to both sides of the equation, and those will cancel out, and I'll ultimately get x1 squared is equal to x2 squared. And at this stage, what I want to do is I'm going to take the square root of both sides. If I do that, that's going to give me that x1 is equal to plus or minus x2. And so because they're not equal to each other, we don't have that x1 is equal to x2. This shows that g of x is not 1-to-1. And we might have already expected that, because if you were thinking about what the graph of g of x equals x squared minus 1 looks like, that's a parabola with a vertex at 0, -1. So it looks something like that. And similarly to example 1, we saw if I drew a horizontal line, it would fail the horizontal line test. So we might have already expected that going into part B. Let's go ahead and solve part C now. All right, so in part C, we're going to let h of x1 equal h of x2, and then we'll get 2 times x1 plus 1 over x1 minus 3 is equal to 2 times x2 plus 1 over x2 minus 3. So what I'm going to do here is I'm going to cross multiply, because I have that a fraction is equal to a fraction, so we can cross multiply. If I do that, we get 2x1 plus 1 times x2 minus 3 is equal to 2x2 plus 1 times x1 minus 3. All right, so we're going to need to do some multiplication. You can either use the box method or the FOIL method. And on the left-hand side, I'm going to get 2 times x1 times x2 minus 6x1 plus x2 minus 3. And on the right-hand side, we'll get 2x1 times x2, let's see, minus 6x2 plus x1 minus 3. Okay. So now we want to combine any like terms. For example, if I added 3 to both sides, that would get rid of that. And if I subtracted this term from both sides, that would disappear. From here, let's see, I could add this to the other side and add this to the other side. And so we'd get 7x2 is equal to 7 times x1. And then from there, if I divided both sides by 7, we would get that x1 is equal to x2. So this shows that h of x is 1-to-1. All right, so for part D, we have y of x is equal to x cubed plus 9. I'm going to set y of x1 equal to y of x2, and that's going to give us x1 cubed plus 9 is equal to x2 cubed plus 9. If I were to subtract 9 on both sides, those would disappear, and we'd get x1 cubed is equal to x2 cubed. And then if I took the cubed root of both sides, now be very careful, the cubed root does not yield the same result as a square root because the index is an odd number, and so we're just going to get x1 is equal to x2, and that shows that y of x is 1 to 1. So in all of these examples, all of them were 1 to 1 except for part B. This was not 1 to 1, and the other functions were 1 to 1 functions. So why are we putting all of this effort into finding out whether a function is 1 to 1 or not? Well, it turns out that the purpose of exploring 1 to 1 functions is so that we may look at something called inverse functions and whether or not those exist. Suppose you decide to go to an engineering conference in Bogota, Colombia. Before your trip, you see that the temperature the day you land is supposed to be 17 degrees Celsius. Fortunately, we have a formula to convert that into Fahrenheit. Fill in the formulas below, then convert 70 degrees Celsius to Fahrenheit. So we do have a way of converting back and forth between Fahrenheit and Celsius. And so in the first box, if I want to convert Fahrenheit to Celsius, we have the formula that the Celsius value is equal to 5/9 times the Fahrenheit value minus 32. And I don't even really need to know what the other formula is, because one thing that I could do is I could plug in 17 for the C value and then solve for F. Or I could do that without even having to plug it in. What do I mean by that? Well, if I multiply both sides of this equation by 9/5, then I would get 9/5 C is equal to F minus 32. And then if I added 32 to both sides, I would get F is equal to 9/5 C plus 32. And it turns out that that's the formula that we were looking for in the next box. So a Fahrenheit value is equal to 9/5 of the Celsius value plus 32. So it's cool that we can go back and forth between those. Let's go ahead and answer the next part of the question. We want to convert 17 degrees Celsius to Fahrenheit. Really, it doesn't matter which one of these formulas we use. It's just going to be a little bit easier to use this one. So I'm going to go ahead and plug in 17 for C. That's going to give us 9/5 times 17 plus 32. And then if we were to simplify that using a calculator, this is approximately 62.6 degrees Fahrenheit. Let f be a 1-to-1 function with domain A and range B. Then its inverse function, denoted with an f and then a superscript of -1. So that inverse function f inverse has domain B and range A, and is defined by f inverse of y is equal to x if and only if. Remember, this arrow, double-sided arrow, means if and only if f of x is equal to y for any y in B. F inverse of x is read as f inverse of x. Now please be very careful. I've put this in big red letters. Be cautious of the following. F inverse of x is not the same thing as 1 over f of x. The -1 is not an exponent. If I wanted to denote 1 over f of x, I would write that as f of x raised to the -1 power, like that. So please be careful. These are not equivalent. Having a -1 in the superscript does not represent an exponent, but rather a notation for inverse functions. So please keep that in mind. Example 3 says, let f be a function defined by the following. F of 2 is equal to 4, f of 0 is equal to 9, and f of 7 is equal to 5. Is f 1 to 1? If so, find f inverse. If not, explain why. So there's a lot of different ways we could represent this function. One way is through a table. So I can have x and f of x. And so it says that 2, when we plug it into our function, our output value is 4. If I plug in 0, my output value is 9. And if I plug in 7, my output value is 5. Now, these are the only values that we can plug into our function. So our domain here, our domain is the set 0, 2, and 7. So those are the only things we're plugging in. And then our range is the values 4, 5, and 9. So it turns out that this is a one-to-one function, which means that from our definition up above, we can find an inverse function. So another way that we could denote this is that this notation, we could say 2 maps to 4, 0 maps to 9, and 7 maps to 5. So since our 3 output values do not have multiple input values going to them, or they have unique input values going to them, again, this is a one-to-one function, and therefore it has an inverse. So there's a few different ways that we can define this. So if I wanted to make a table, I could say x, and then I could say f inverse of x. So now we're taking all of the output values and we're mapping them backwards, basically. So for example, if I plugged in 5 into my inverse function, that would map to 7. If I plugged in 9, that would map to 0. And if I plugged in 4, that would map to 2. So, and another way that we could denote this is here we have these values. So for the inverse function, we would say that, for example, f inverse of 4 is equal to 2, f inverse of 9 is equal to 0, and f inverse of 5 is equal to 7. So that's another way that we could denote this. So a question down below says, why do you think that a function cannot have an inverse if it is not a one-to-one function? Well, let's go back to an image that we saw before. So here, this function where we have a person gets mapped to the city that they were born in, that means that if I were going in the other direction, if I were coming up with some function g inverse, what this would do is this would take a city and the city would represent the input value, and then the output value would be the person or persons that were born in that city. So if I were drawing arrows then, let's see. So if I were going in the reverse, in the inverse function, that would be like saying g inverse of Oakland is equal to Zendaya. G inverse of Oakland would also equal Kamala Harris. But that would defy the definition of what a function is, because we can't have a single input mapping to multiple different outputs. So this is essentially answering the question, if a function is not one-to-one, then it cannot have an inverse function because of the definition of a function. Example 4 says, suppose that f of x is equal to x squared minus 1, with the domain of f being the set of positive numbers. So with the domain of f being the set of positive numbers, remember from before in an earlier section, this is what's called a restricted domain. Because normally, when we're thinking about this quadratic function, normally it has a natural domain of all real numbers. for this particular function because a quadratic is a polynomial, and all polynomials have a natural domain of all real numbers. So what we're doing here is we are restricting our domain to be only the set of positive numbers. So in part A, we're wanting to find f inverse of 8. In other words, in our regular function, we're essentially asking f of what value gives us 8. So one way that we could figure that out is we could set our output value equal to 8 in our formula, and we can solve for the x value. If I add 1 to both sides, I would get x squared is equal to 9, and then if I took the square root of both sides, I would get x equals. Now at this point, typically we would put plus or minus, but in this case, remember, our restricted domain is the set of only the positive numbers, so we're going to get x equals 3. So all of that was to say f inverse of 8 is equal to the number 3. Part B asks us to evaluate f of 8 to the negative 1 power. So hopefully something that you might recognize is this has nothing to do with inverse functions. It's not using inverse function notation. The negative 1 here does represent an exponent because it's not the superscript of the f character. So what we want to do is we want to evaluate f of 8 and then raise it to the negative 1 power, which, if you remember from properties of exponents, that's the same thing as 1 over the value of f of 8. So I'm going to come up here and I'm going to evaluate f of 8, which is equal to 8 squared minus 1. 8 squared is 64, minus 1 ends up being 63. So this is equal to 1 over 63, and that's our final answer for part B. Part C also has nothing to do with inverse functions because the negative 1 again is representing an exponent. So this is the same thing as f of 8 to the negative 1 power, which is the same thing as f of 1/8. If I plug that into my function, that's going to give me 1/8 quantity squared minus 1. 1/8 squared is 1 over 64. If I find a common denominator, that is equal to 64 over 64. And so that is ultimately going to be equal to negative 63 over 64. So that's our final answer for part C. And that concludes example 4. It turns out that there's kind of this systematic way for finding a formula for an inverse function, and here's how it goes. Suppose f is a one-to-one function. To find a formula for f inverse of x, 1, we replace f of x with y in the original formula for f. 2, we swap the location of y and x in the previous equation. 3, we solve your new equation for y. And then lastly, we replace y with f inverse of x. Let's put this set of steps into practice. Example 5 says, consider the given functions. If they are one-to-one, find their inverse function. So here we have a cubic function. We saw in a previous example where we graphed x cubed. That was a one-to-one function. The +4, all that does is that shifts our graph up 4 units. So that would still pass the the horizontal line test. So this is a one-to-one function telling us that this is going to have an inverse. So for part A, I'm going to replace f of x with y. This is my first step, or step 1 here. Step 2 tells us to swap the location of x and y, so I have x equals y cubed plus 4. Step 3 wants us to solve for y, so I'm going to subtract 4 on both sides, and that's going to give me x minus 4 is equal to y cubed. And if I'm solving for y, I can take the cubed root of both sides. So I will take the cubed root of this side, and I'll take the cubed root of this side, and that will end up giving me y is equal to the cubed root of x minus 4. And then my last step is I just want to replace y with the notation of f inverse. So f inverse of x is equal to the cubed root of x minus 4. So that's our final answer for part A. All right, so for part B, we have g of x is equal to 2x minus 2 over x plus 1. Now, at this point in time, we haven't extensively covered rational functions, so we might not know what the graph of that thing looks like in order to tell whether it's a one-to-one function or not. However, we did go over an example similar where we were using algebra to determine if a function is one-to-one. I'm not going to go over that here, but we did go over that a few examples ago. So it turns out that g of x is a one-to-one function. So I'm going to go through the steps to find its inverse function formula. So for part B, step 1, I'm going to replace g of x with y. And then for step 2, I'm going to go ahead and swap my instances of y and x. So I'm going to get x equals 2y minus 2 over y plus 1. And now my goal is to solve this equation for y. So I'm going to multiply y plus 1 to both sides of my equation. If I do that, that ends up giving me x times y plus 1 is equal to, these are going to divide out, and I have 2y minus 2. And then I'm going to distribute in this x. If we do that, we get xy plus x is equal to 2y minus 2. I want to get all the y terms on one side, so I'm going to subtract x from both sides. And then I'm going to also subtract 2y from both sides. So that's going to give me xy is equal to, xy minus 2y is equal to negative x minus 2. And from here, on the left-hand side, both of those terms have a y in it, so I can factor out the y. And the right-hand side does not change. So then if I divide both sides by x minus 2, we get y equals negative x minus 2 over x minus 2. Now please be careful, you can't really cancel out anything here, but if I wanted to make this look a little bit nicer, one thing I could do is in the numerator, I could factor out a negative 1. If I did that, that's going to leave me with x plus 2. And in my denominator, I still have x minus 2. And then if I distributed this negative 1 into my denominator, just again to make this look a little bit nicer, we could say that this is y equals x plus 2 over negative x plus 2, or 2 minus x. And then finally for step 4, this was all step 3. So maybe I'll put step 3 here. And then for step 4, we can replace g inverse of x is equal to x plus 2 over 2 minus x. So here is our final answer. The inverse function property says, let f be a one-to-one function with domain A and range B. The inverse function f inverse satisfies the following cancellation properties. So if I compose f inverse with f, that is going to end up simplifying to x for every x in the domain of f, which is we called it A. And then if I compose it the other way, it'll also equal x for every x in B, which is every value in the range. Example 6 says, consider the functions f of x equals 12 plus 2x and g of x equals 1/2 x minus 6 are f and g inverses of each other. So based on this property, one way that I can check if these two functions are inverses of each other is by composing them. So let's see what happens. If I do f compose with g of x, that is equal to f of g of x. So I'm going to take 12 plus 2, and then instead of x, we're plugging in g of x, so that'd be 1/2 x minus 6. And let's simplify that. I'm going to go ahead and distribute the 2. So that's going to give me 12 plus x minus 12. And if we combine like terms, that ends up equaling x. Let's do it the other way around. So if I compose it the other way, that's going to be equal to g of f of x. So that's going to give us 1/2 times 12 plus 2x minus 6. If I distribute the 1/2, that's going to be 6 plus x minus 6, and then combining like terms we get x. So notice that we got x both ways that we compose this. So by the inverse function property above, we have shown that f and g are inverses of each other. Example 7 says, consider the function f of x equals x squared plus 1. Let's restrict the domain to 0 to infinity so that f is 1 to 1. Find a formula for f inverse, then graph both f and its inverse on the grid provided below. Then identify the domain and range of f inverse of x. So normally x squared plus 1 is not a 1-to-1 function. We saw that previously, but what we're doing is we're restricting the domain so that it's just between 0 and infinity. And if we do that, then we are making f a 1-to-1 function, which means that we'll be able to find an inverse for it. So step 1, if I want to find an inverse function, I'm going to replace f of x with y. Step 2, I'm going to swap the location of x and y, so I get x equals y squared plus 1. And then step 3, I want to solve for y. I'm going to subtract 1 from both sides, and that would give me y squared is equal to x minus 1. And now I'm going to take the square root of both sides. That's going to give me y equals, and again, normally we would put plus or minus, but in this instance, we only have the positive values, so it's just going to be y equals the square root of x minus 1, and then step 4, I'm going to replace y with f inverse of x. So here is our formula for our inverse function. Let's go ahead and graph our two functions, our f and our f inverse. All right, so I've went ahead and I've graphed our two functions f and f inverse. Now it says identify the domain and range of f inverse of x. And if you remember from properties earlier, when you are finding an inverse function, it basically swaps the domain and range of the original function. So our original function was f of x equals x squared plus 1. Its domain, we already found, was restricted to 0 to infinity. And then the range of this would be, notice that the y value here starts at 1. And then goes off to infinity. Okay, so then let's talk about the inverse function then. So f inverse of x is equal to the square root of x minus 1. And so its domain would be 1 to infinity, and then its range would be 0 to infinity. And we also could have solved that. Since it's a square root function, we could have set our radicand to be greater than or equal to 0, and we also would have gotten this same domain. But notice here the relationship is that the domain here becomes our range for our inverse function, and then vice versa, our range becomes the domain for our inverse function. What do you notice about the relationship between the graph of f and f inverse in this example that we just went over? Pause the video here and take a minute and ask yourself, what's the relationship, or what kind of pattern do I see between these two graphs? And I'll go over the answer in just a minute. So to answer the question, what do you notice about the relationship between the two graphs of f and f inverse, is that they are actually symmetrical about the line y equals x. So if I graphed y equals x here, I'm trying to do this as straight as possible. Okay, so this is the line y equals x, and notice that they're symmetric because essentially what we're doing is we're swapping all of the x and y coordinates. So for example, this here is 0, 1, and then to get this point, we have 1, 0, or take for this one, this is 2 comma 5, and then this is 5 comma 2. So again, to answer the question, f and f inverse have graphs that are symmetric about the line y equals x. Example 8 says Mr. Kwan opens up a pizza shop where he charges a base price of $15 for a large cheese pizza. $50 would be a lot. And then $1.25 for each additional topping. Part A says come up with a function f that models the total cost if you get x number of toppings. So if the base price is $15, then I'm going to come up with a function f of x where x represents the number of toppings you get. So we have this base price of $15 plus $1.25 for every additional topping that we get. So hopefully you're able to recognize that this is modeled by a linear function. So that is the answer for part A. Part B says find f inverse. What does it represent? So I'm going to go ahead and have y equal 15 plus 1.25x, and then I'm going to swap the location of x and y. And now I want to solve for y. I'm going to subtract 15 from both sides, and then divide both sides by 1.25, and that's going to give me y equals x minus 15 over 1.25. And now my last step is I just replace y with f inverse. So finally, after we've gotten this point, now I'm going to change to the inverse notation. So we have f inverse of x is equal to x minus 15 over 1.25. And here is our inverse function. When we say what does it represent, our input for this is the total cost of our pizza, and then it will tell us how many number of toppings we got. So this function tells us how many toppings we got based on inputting the cost of the pizza. So that is it for part B. Part C says if a pizza costs $25, how many toppings does it have? So for part C, we are wanting to evaluate f inverse of 25. That's going to equal 25 minus 15 over 1.25. And that ends up simplifying to 8. So that tells us that if a pizza costs $25, that means that it would have had 8 toppings. And that's it for example 8. Example 9 says below is the graph of a function g of x that is a combination of transformations of the function f of x equals the square root of x. A hint is that the only types of transformations are shifts. Part A says find g inverse of 4 only based on the graph above. So here what I'd like to do is I'm going to label my y or output values here. So here's 4, and I can see that this ordered pair right here on my graph is 5, 4, which tells me for my regular function that g of 5 is equal to 4. And what that tells us is this implies that g inverse of 4 is equal to 5. So that is the answer for part A. Part B says come up with a formula for g of x. So it says here that the only types of transformations are shifts, and we're transforming this parent graph here. So we can see that this part is shifted right 1 unit and up 2 units because the square root of x normally starts at the origin. So that means that g of x, this is part B, g of x is equal to the square root of x minus 1 and then plus 2 since we're shifting up 2 units. So that's our answer for part B. So for part C, we want to come up with a formula for the inverse function of g. I'm going to say y equals the square root of x minus 1 plus 2. I'm going to swap the location of x and y, and now I'm going to solve for y. I'm going to subtract 2 from both sides. Then I can square both sides. And finally, I can add 1 to both sides. And now I have g inverse of x is equal to x minus 2 quantity squared plus 1. So part D says graph g inverse on the grid above. Before we do that, I want to go back and define the domain and range for our original function. So we have g of x here. Our domain is, I could only plug in numbers that are 1 or larger because we're dealing with this square root. So my domain is going to be 1 to infinity. And then we can see that our range is starting at 2 and then going off to infinity. Why am I bringing this up? Well, this here, our inverse function, is a quadratic. And normally for a quadratic, the natural domain is all real numbers. But if we graphed that, that would not pass the horizontal line test. So remember, when finding an inverse function, our domain and range swap from the original function. So for our inverse function, its domain is going to be 2 to infinity. And then its range is going to be 1 to infinity because I just swapped what we had from our original g function. So that's going to help me graph it now. I know that it's a parabola with its vertex at 2, 1. So that's going to be right here. And I can plug in numbers 2 or larger. So if I plugged in 3, that would give me an output value here. And then 4 would be here. And I know it's kind of like half a parabola, and it's going to look something like that. And just like before, if I were to graph y equals x, notice that they are symmetric about both of those. So I've gone ahead and I've graphed our inverse function here. So thanks for watching. That concludes this video on one-to-one functions and inverse functions.